between this conductor. We use the right hand rule. You know, if I hold my hand such that the B is entering to my palm, right here. So you look at, if I hold my hand this way, B is entering here, right? And my thumb is showing the direction of the movement, right? The four fingers here, they're going to show the product. So basically, in this case, let's not do it this way, it's easier. Let's say it's moving this way. Let's say it's moving this way, right? Now, look at here. B is going this way. This one is moving this way, right? The polarity here is like this, right? This is a generator, okay? It's not a very good generator, right? You guys, you use some mechanical power, you move this one, right? What is going to happen? You're going to generate electricity, right? If you close this switch, you're going to have a load here, right? If you don't close the switch, you have only you have a potential here, but it's not generating any voltage. What is how much is E? E is equal to V cross D times that. So you know this is what we call this one? We call it is it inner product? We call this one cross product, something like product. What's the name for that? So basically, if you are going to find out what's the direction of this one, right? This one is going to be end up a vector, right? It's a vector. How much is that vector? Is the magnitude of vector, you know this, V times B is, because I'm going to put the value of this one, you know, I'm not going with the direction for now. It's going to be the amplitude of V times the amplitude of B, right, times the sine alpha. What is the alpha? Alpha is the angle between B and V, right? So, but what is the direction of this vector? Think about it. So, I'll put my forefinger in the direction of B, and let me see. I need to rotate it to B. B is this way. B is this way. So B is this way, right? V is this way, right? Look at here. This is a B, and V is this way, right? If I rotate B, I'm not sure, was it B to V or V to V? I believe it's a. I think I'm not sure. If this one rotate to this one, or this one, or this one rotate on this one. But let's say you go B to the V. So this is a B, right? This is a V this way. So if you rotate B to the V on V, so it's going to be a vector pointing down, right? I think I'm wrong. It's going to be other direction.
It should be
but I think it's going to be this one will be rotated toward this one. So basically, if you look at it, B this way, B this way. If you rotate this one, it's going to be a vector this direction, right? So how much is the value? This much. How much is, what is the direction? This one, right? How about L? L is the length of this one, right? Is this way also, right? Is the inner product. It's going to be amplitude of this vector times amplitude of this vector times cosine of the angle between this vector and this vector, right? Now let's look at this one. How much is alpha? See, this is a V, this is a B, right? 90 degrees. So basically, this one is going to be how much? 1. So let's call it the amplitude of V, call it V, and call this one B, right? The amplitude of this two. How much is the angle between this vector and L? Vector L is this way, right? V times B also is this way. So the angle between L and V times B is how much? 0. So cosine 0 is going to be 1. So basically, this one is going to be V times B, whatever is this value, times L times cosine, wait, is the beta? Beta is 0. How much is this one? Is VB. How much is the amplitude of L, vector L, is L, the length of the wire, right? So basically it's going to be VL, right? This is the induced voltage in this conductor, right? Induced voltage in this conductor, right? This is generators works based on this one. You have a conductor is moving in a magnetic field using a mechanical force, so it's going to generate electricity. So we are converting mechanical power to the electrical power.
What's the direction of alpha again?
Alpha is here. See, we said V times V cross B is a vector like this, right? Vector like this, right? And L is a vector like this also, right?
Oh, okay.
This is a L, this is a length, and the vector we consider the positive direction of this one toward up. You can consider it down, it doesn't matter, So basically this one is going minus. The amplitude is going to be down,
Okay.
based on which direction you define for the L positive. But we consider the positive direction positive for this one. Now, usually in the electric machine we don't have one conductor. I want to go through one more thing. Let's consider the same thing. Now my conductor is like this. And is moving this way. This one is moving B this way. We know B is here. Now, let's see how much is the induced voltage in this winding. This one we know how much is. How much is this one? E, right? Actually, this one is not going to work well, But see, we consider this one. So we go from here to here to here. This is the direction of things, right? In the electric machine is rotating, one is going one direction, one is going the other direction, but here, most of them are going, again here is going to be E, that's fine, Right, because this is the same thing here, right? This conductor is moving this way, B is here, and V is here, so we are going to have the same voltage. How much voltage we are going to have here? Induced voltage. Is 0. Why is 0? Because L, see, L is this way, right? The direction of L is this way. Still BV is going to be this way, right? BV is this way, so basically 90 degrees is 0. How about here? V induced. So my point is, see, this one, being there or not, from the voltage induced, voltage generated doesn't matter. So that's the reason when you look at all these electric machines, they have an end winding. I'm not sure how many of you have seen the electric machine open, So I'll bring some pictures, from Google, maybe next class you can see. The end doesn't matter, There is a, usually they are cylindrical. We have a loop like this. One goes to, for example, the upside of the, if you look at the machine, is like this, a spindle. Just across this one. They have one slot here, one slot here. So they put this one here, down here. They put that one up there. So this part is going to come from this side, come down. This part is going to be on the other side, right? But it really doesn't matter because it doesn't generate any power. Ideally, there is a little bit, but not that much, So because these are the end windings, no effect on what you are generating or consuming, right? So these two, they are important. These two leg guys. We call this one, this is a one turn, you can see, and we call this one conductor. Each of these legs is called a conductor. One turn, and each of this one is one conductor. Basically, one turn is a two conductor. If you have an n turn, think about it. Maybe this one was I don't know, 20 turns, right? Overall, you are going to have 40 conductors, double of number of turns, right? These are basic rules for the generator. How do they work? Let's talk about the motor. How motor works. We said in generator, we have a conductor is moving in a magnetic field. Can you tell me what's the rule for the motor before going through the equation? For the motor. I think you had this. I believe you had this test in the physics. You know, they said they put the magnets here, for example. I'm not sure. When we were in high school, we had this one. We have an S here, and say build a kind of structure like this. This one is fixed here, and put a wire here, like this. The wire is coming here, and this wire is going through a source here, and there is a resistor here and a switch here, and a switch here. Now, this wire is kind of fixed here. As soon as I close this switch, what is going to happen? No?
Turn.
What?
What charge is it going?
So we're going to have a current here, yes. What's going to happen?
A magnetic field.
The magnetic field is there. It's a permanent.
No, a magnetic line.
The wire is going to start to move, either this way, now I don't know which direction, but it's going to start to move, right? So basically, why is moving? So there's a force here, right? The movement happens because of force, right? So basically, when you have a conductor carrying current in a magnetic field, it's going to generate force, right? That's the main rule for electric machine. Electric motors. You have electric motors. Either it's a permanent magnet, this magnet is here, or somehow it's built inside the machine. So you have a one field. So you plug it to the wall. When you plug it to the wall, you generate the current through the conductors. When the conductors, they start to carry current, they're going to generate force. Force is going to generate torque, and the machine is going to start to move. That's the basic of the electric motor. In generators, you have a magnetic field. You move the conductor, generate electricity. In electric motors, you have a magnetic field. You put the current going through the conductor, it's going to generate the force. So here, you put the electrical energy to the conductor, it generates force and movement, which is a mechanical energy, right? So basically, the motor is electrical to mechanical converter. Here, we moved this one, which is the mechanical energy, right? This movement ends up to generate electricity, which is the electrical energy. So generator is the mechanical to electrical converter, right? So let's go through the rules for this one. Let's say we have a magnetic field here, B is like this. We have a conductor here, length is L. The same thing like over there. This one is B, right? And length is L. We put some current, let me use the right direction for the current. For this one, we use the left-hand rule. For the generator, we use the right-hand rule. For the motor, we use the left-hand rule. So we said again, if the magnetic field is referring to my hand this way, right? So if these four fingers, showing the direction of the current, then the thumb is going to show the direction of the force. Let's put the current. Let's say we have a current like this in this one. Right? So I want to see which way this conductor is going to move. I'll bring you the question I gave it to the last year exam to see how simple it was. It was maybe 5 letters or 6 letters, but very conceptual, to find out. I gave them one exam. I said, tell me this is a motor or generator. I will bring it down. Hopefully I'll remember to really make time. So basically that was all these rules, you know. You have a direction, you know, you find out what's the force or torque. Force and torque, they are the same. Now when you have the force and torque, I give the direction of the motor. You have to calculate that one. If it's in the same direction with the speed, you say this is the motor or generator. If you find out force or torque is in the same direction with the speed, it's a motor, right? Yes. That was as simple as this one. Just they need to use this left or right hand rule. Find out what's the direction of force, and look at it. If it's the same direction with the motor, it's with the rotation is a motor. If it's opposite of that, is generator, right? That was as simple as this one. But maybe 5 to 10% answer the question. You know, it takes maybe 3 minutes maximum if you're going to think about it, you know. But I saw people, they wrote a book about it in the exam, you know, to say what it is. But they still didn't answer the question what they should answer.
You said same direction as what? If it's a motor?
Yeah. So we said, let's
Same
look at
direction as for
the speed.
Okay, the speed.
Yeah. So now, here we have a current this way. We have a magnetic field this way. I use my left hand. So magnetic field is going this way. Not this way. Remember, it should go this way. Okay. So the magnetic field is going to my hand. The forefinger shows the current direction. So the force is going to be this way. This is the force. Basically, this conductor is going to move this way. If you have something like this, the conductor is going to move that way. The example, I put it on the board now, I can tell you what was the direction. Remember, it said here N, right? It said here S, right? And we had this wire here, and the current, if you remember, the polarity was up there. So the current was like this, right? If you are going to find out what's the direction of the movement for here, you say B should go here, right? B is going to go from N to the S, right? This is a B. You know, inside the magnet is from S to N, right? Outside the magnet is from N to S, right? That's a B. So B is going to go this way, B is going this way, right? I is this way, so the conductor is going to come this way, it's going to move this way, toward outside of it. No, here. See, look at here, the current is going this way, the field is going to go this way, so this one is going to move this way. If the current was the other way, it's going to go like this, right? So this is how we can figure out which way the conductor is going to move. Now, I'm not going to go through the detail, very simple. You know, F is equal to I times, and this is again vector of I, LB. B is this one, L is direction again this way, I is the same direction here with the L. So basically, if you simplify this one in this case, it's going to be B, let's make this one B-I-L. That's it. I'm going to use these two rules to get to the equation of the DC machine. Now, if I have 10 conductors next to each other here, each of them is carrying I current, how much is my force? If I have 10 conductors. 10 times, right? Each of them, they're carrying R, right? So basically just times it by 10, right? It looks like you have one conductor, current is 10 times, right? Instead of current I is 10I, right? What I'm saying here, can you tell me where I'm going? So if I want to have more force or more voltage, it's proportional to current and no, it's torque is proportional to current and number of turns, exactly, L, right? L is related to the number of turns, exactly, right? So if you want to have a very high torque machine, right? One way is to put a huge current to the machine, right? But there is limitation. By your source first, right? Let's say you have this outlet here. It can give us maximum 16 amps, right? Now I want a torque equivalent of 10 times of this current. What should I do? I'm going to put it 5 turns. 5 turns is going to end up 10 conductors, right? 10 conductors times this current looks like one conductor 10 times of this current, right? So to increase the force or torque, either you can increase your current or you